We're almost there. 6 lessons to go. This one takes the net change theorem, which was our last lesson, and kind of emphasizes its importance by showing 2 questions that could potentially be a full page on your final exam. I have blatantly stolen these from AP exams. So I model my long questions on AP questions. You are free to search the internet for AP Calculus, AB free response questions, and anything you find is good to help you study for us. So this is a question about Janet's driveway. If you've done this lesson the way I've asked you to do this lesson, you have already looked at this question. And that's important because I'm going to talk about it as if you have already seen the question. So we know that snow is falling according to some rate, and snow is being shoveled according to some rate. So this is a question about how rates play together. Calc 1 is all about rates. And so let's go. How many cubic feet of snow have accumulated on the driveway by 6 a.m.? So what does it mean to accumulate? Well, we're just looking for what snow fell. We're not looking for what snow has been removed or what the net amount of snow is. We're asking what snow fell. So this talks about how snow falls. In fact, let's get better with this. So this is snow falling, and this is snow being removed. We are interested in snow falling. So because we're interested in snow falling, we're going to concern ourselves with this rate, and it starts falling at midnight. We're interested in 6 a.m. This is cubic feet per hour. We're interested in cubic feet. We've got to remove a layer of time. And this is what removes a layer of time. So we integrate f of t dt from 0 to 6. The calculator does this. There is not a good way to do this without the calculator, so we type all the buttons and we get 142.275 cubic feet. This is the sort of thing where if you cannot get your calculator to do that, you should stop by in an office hour and ask, because that's a big deal. And it's an easy way to pick up a bunch of points. So let's talk about the rate of change of the volume of the snow. So we know that snow is falling, and we know that snow is being removed. So if we're talking about the rate of change of the volume of the snow, this plays a part, this plays a part. So if we knew how fast the snow was falling and we knew how fast it was being removed, we could subtract them. And that's what we're going to do. Again, your calculator is helpful. We know what this rate is. We know what this rate is at time equals 8, at time equals 8. The calculator does that for us. We get negative 59.583 cubic feet per hour. What does that mean? That means that G of 8 is bigger than F of 8. That means that at 8 a.m., more snow is being removed than is falling. So the amount of snow on the driveway is going down at time equals 8. Okay, so now let's take a look at what Janet has removed from the driveway. So again, we're not going to pay attention to how much snow is falling. We're just looking at what Janet has removed from the driveway. And we're asked to express h as a piecewise defined function. And I imagine that these are the pieces. So let's just set that up. There's going to be one thing for times less than 6. There's going to be one function for times between 6 and 7, and there's going to be another expression for times between 7 and 9. So let's do the easy part first. Janet is not removing any snow before 6 a.m. Janet has not removed any snow before 6 a.m. Now let's consider between 6 and 7. Janet is removing snow at 125 cubic feet per hour. And that's linear. This derivative is a number, which means that this function is a linear function. This is the derivative, so this is the slope, right? And then all we need is the y-intercept. Well, what's the y-intercept going to be? We know that at time equals 6, Janet still has not removed any snow. So if time equals 6 here, this has to be 0. Well, at time equals 6, this part is 750, so we subtract that 750. If you want to think about this in a different way, and I'm going to write this and then erase it. If you want to think about this in a different way, Janet is removing snow at 125 cubic feet per hour. So if we look at how many hours have gone by since 6 a.m., that would be how much snow Janet has removed, and that happens to be 125t minus 750. So hope that's helpful. The same sort of thing is going to happen down here. The slope is 108, so this is definitely 108t minus, well, this gets a little bit tricky because we know that at time equals 7, we've got this much snow on the driveway. And so we can figure that out and play the subtraction game, and we get a similar response here. Again, I'll write and erase. There's 125 cubic feet of snow that Janet has removed in this hour. And then she's going to slow down a little bit and remove 108 cubic feet of snow for every hour past 7. And this simplifies to that. So that's where that comes from. Hope that's helpful to you. This is a piecewise defined function. Domain up to 9, got to include 9. And then the D part, before we depart, how many cubic feet of snow are on the driveway? Well, what affects that? What affects that is how much snow has fallen and how much snow has been removed. So how much snow fell between midnight and 9 a.m.? This much snow fell between midnight and 9 a.m. Then how much snow was removed before 9 a.m.? Whatever h of 9 is. You throw that 9 in there, boom, you got it. The calculator is super helpful to you here. There are 26.335 cubic feet of snow on the driveway at 9 a.m. This is an 18-point question. 4 and 4 and 6 and 4 in my class. 4 and 4 and 6 and 4. This could show up on your final exam. No doubt about it. Something like this could show up on your final exam. Similarly, something like this could show up on your final exam, and it wouldn't be too crazy terrible. So this is the rate at which cars turn left at a particular intersection, and so we're looking for the total number of cars turning left. So if this is the rate, and we're interested in the total number, this is definitely an integral from 0 to 18. I mean, without a doubt, we know the rate at which cars turn left. We're interested in the total number. Without a doubt, that's an integral. When in doubt, it's an integral, and the calculator does it for you. Then things get a little weird. Average value of L. Like, we know what an average value is. We know that the average value of a function is its integral divided by the length of the interval. That's how we find average value of a function. The average value of a function is its integral divided by the length of the interval. The question is, when is this true? So we graph 150 and see where those spots are. It turns out that this spot is 12.428, and it turns out that this spot is 16.122. So we integrate from 12.428 to 16.122, and then we subtract 16 to minus 12. The calculator helps us out with that, and we get 199.426 cars per hour. Does that make sense? Here's 199.426. Does that look like about the average of this? Probably. So it's a reasonable answer. And then in the C part, so we're interested in installing a signal if the product of the total number of cars turning left and the total number of cars going straight is greater than 200,000. And we know that this many cars travel straight. So I don't know why the folks in New Jersey thought to obscure this in this way, but all this means is that the integral from some point to some other point has to be bigger than or equal to 400, because 400 times 500 is 200,000. So if we can find an integral from some number to some other number that's 2 hours ahead of that, and that integral is greater than or equal to 400, then this product will be greater than 200,000, and yes, we need a traffic signal. So what would that mean? Well, this has to be at least 2 hours, so I'm imagining that this would have to be 200 or more, and it turns out that if A is 13 and B is 15, then this is true. And so yes, it needs a traffic signal for the reasons I have outlined. This turns out to be 4 points, 8.6 points in my scoring system. This could be a question on your final exam. What's the big takeaway here? When we have rates and we're interested in total numbers, it always turns into an integral. When we're looking for the average value of a function, we always use the integral. These are things that you should be aware of because they're going to pop up again and again, and that's my hint to you. Okay. Thanks, everybody. Hope this was helpful. Stop in on an office hour if you need a little bit extra. No problem at all. I make myself available for you. See you soon.